So as I mentioned previously, the plan for today is to discuss all of midterm and particular focus on the practice midterm. Okay. Some people are having trouble connecting. Okay. All right. But first, I'm just going to do a quick rundown on, even though you can see from practice, here are the things that you should be able to do for the regular problems. Okay. And I'm typing these out in the order in which I think of them, not necessarily the order that they appear on the desk. All right. So first, rate of convergence. Function of h as h goes to 0. All right, so this is from 2.1. Okay. Second, deal with the fix expression to take care of catastrophic cancellation. Next, given x and y values, compute the interpolating polynomial in either Lagrange or Newton form. That's 2, 7.3. And finally, an upper bound for the error in the interpolating polynomial. So it feels it's 7.4. Either on an interval or at a point. So for the error formula, which here it is. Now, if it asks for the error on an interval, then x can be any point within the given interval, and c is an unknown point that also would fall within that interval. Okay. Oh, sorry. No. C falls within an interval containing the interpolation points. In this case, I chose the interval 0, 1, which includes the interpolation points. Okay. If it asks for the error interpolating polynomial at a single point, then you would plug that x value in here for x. But this unknown point still can be any point within an interval containing all the interpolation points. So that's important to keep in mind, that the distinction between c and x. So no matter what, in a portion of the error formula, n plus first derivative of f at c it can be any point within an interval containing all the interpolation points. So in that case, what you want to do is find out how large this can get on such an interval. Okay, so for regular problems, we're just worth half the points in the test, 50 points. These are the things that will come up, and you solve them on a practice test. So the rest is, of course, like concept checks, questions like you see on the quizzes. Here's one thing that I want to bring up. So it's actually a little bit of a oversight on my part. That it turns out that there is no distinction on the midterm for students who are in 460 versus 560. So for graduate students, it is supposed to be taken up a notch. And unfortunately, I simply forgot to do that. By the time I thought about it, it was after I'd already put out information about the midterm and explained what it was going to be like for everybody, and therefore I didn't want to go change it. I will not make the same mistake for the final. So what I would do in that case is I would put on the test a certain number of problems and say, like, okay, undergraduates have to do this many, but graduate students have to do this many, something like that. Years ago, what I would do is I would apply like a curve for undergraduates. Then I was told that I should not do that. So I'll get to all later. Okay, now, floor is open, so any questions that you might have about the practice or just about the midterm in general. If we don't have any more questions on that, we can talk about homework as well, but so whatever you got.
All right. I don't know if this is, you'll have to tell me if you can, or
Okay.
at least maybe work a similar problem, I don't know. But fix a mathematical expression to reduce catastrophic cancellation. That is certainly one on this on homework.
That's the one I was about to ask about.
But I realize that not everybody's at the same point of homework. But yeah, I don't know.
Let's see. So, yes. So, for example, algebraic manipulations like if it involves square roots, multiplying and finding out a conjugate.
Yeah.
Things like that.
Maybe not like, I don't know. I was just gonna ask about that one because this one.
Actually, you know what? I think I was doing another problem. Oh, okay. I can make up a problem.
Okay. Yeah, that'd be great.
Okay.
Yeah.
How helpful this will be, I'm not sure, but wait, I think I saw something in the chat. Okay, the question in the chat, will there be any Matlab functions on the test? No.
Thank God.
You can act as if Matlab is not a thing. Okay. All right, so the original expression we'll work with actually comes from approximating a derivative. So the difference quotient, sine x equals h minus sine x over h. Okay, so one aspect of the question is, when is there a risk of cancellation? So this suffers from cancellation error. Under what circumstance?
When h is very small.
Yeah, when h is very small. So h is one way of writing it, much less than 1 absolute value. Okay, yeah, because then these two numbers are very close together, and if x is not particularly small, that these numbers are not near zero, but their difference is near zero. So the result is smaller than the numbers being subtracted, so that's when that's right for cancellation error. Okay, so the question is, what can we do about it? What's another way that we can write this expression so that it's equivalent, but would not feature this troublesome subtraction? Any ideas?
Taylor expansion.
What?
Taylor expansion.
Well, the trouble with Taylor expansion is that there's going to be a remainder term, so we're introducing an approximation. We want to keep this exact.
Can we try using the sum rule for sine?
Yes, trig identities.
Shallow here, let's
What?
I'm just glad he spoke up before I said something dumb.
Okay.
Go ahead.
Sine x plus h.
Well, it's a good service to provide to your fellow students, I guess. Okay. All right, yeah. So trig identity was the for a sine of the sum. Okay, so that would be sine x cosine h plus cosine x sine h all minus sine x. Okay. All right. So then what we can do with that is all right. So first this term we have cosine x sine h over, whoops, that's supposed to be a numerator, cosine x sine h over h from the second term here, and then I'll write the others in a separate fraction. So we have sine x as a common factor, and then we have cosine h minus 1 all over h. Okay. All right.
Cosine h minus 1 is also.
Yeah, same problem.
Yes.
Because as h goes to 0, cosine h goes to 1, so we're subtracting, again, two numbers are very close, so we've shifted the cancellation error into a different expression. Okay, and this part we don't have to worry about anymore. Any ideas on what we can do with this? Okay, so now you're going to make the problem smaller. Because the rest of it we don't have to worry about. Okay.
If you let h equals 2 times some other number, isn't it like a formula for?
Can we use cos to h trigonometric identity?
Yeah, so there's another trig identity that's known as a half-angle formula. Okay. And that is, I'm going to do it like this so I get it right. Sine theta, or sine squared theta, is equal to 1 minus cosine 2 theta all over 2. So here is a situation where h is equal to 2 theta. So what we get from there is going to be minus 2 times sine squared h over oh wait, I forgot about the h. Okay. theta, so theta is equal to h. Okay. Questions about that? Does that solve the problem? Because now we don't have a subtraction anymore. What's interesting is, since this is meant to approximate the derivative of sine, as h goes to 0, sine h over h goes to 1, so we're left with cosine x. And then for h small, sine of h over 2 would be approximately h over 2. So this whole expression turns out to be approximately minus h over 2, which would go to 0 as h goes to 0. So this term, as h goes to 0, this whole term would go away. And we'd be left with cosine of x, as we should be. All right, so yeah, so for a trigonometric expression, consider using trig identities to deal with cancellation error. And if not, then use your algebraic tricks. Conjugate, common denominator that came up in the homework, things like that. All right.
Excuse me, sir.
Yes.
I was wondering if it makes any difference if we substitute cos h minus 1 over h in terms of cos squared h over 2.
Okay, so replace what again?
Instead of minus 2 over h sine squared h, if we substituted it as, that's okay, it's the same term.
Oh, okay.
Maybe it's the same term.
All right. Well,
I was just wondering if we could use cos squared h over 2, that's
oh,
all.
I see. Yeah. Like sine squared is 1 minus cosine squared?
No, it can be written in two forms, so just that.
Oh, okay, yeah. All right. Okay. All right. Well, oodles of time. Other questions?
Could you do a rate of convergence example?
Okay. See what we can make up here. Okay. Have to be careful. I don't want to accidentally give a 1 from a real test. Okay. I want to put something here. All right. I need to cheat for a little bit. Okay. Okay, so sine h minus h cubed over 6, all over h to the 4. Okay. So first it's a matter of figuring out what is the limit as h goes to 0. Now there's different ways of doing this, but anyone suggest a way of computing the limit? So forget about rate of convergence for now, but just knowing what the limit is.
Well, it all looks like forms of 0 over 0, right?
L'Hopital's rule.
L'Hopital, yeah, that's right.
Yeah, L'Hopital's rule. So, yeah, because if you just let h go to 0, you get a indeterminate form 0 over 0. Alright, so then you would take the derivative of the top and bottom. So we have, okay, until you get something that can be evaluated or until it no longer fits the assumptions of L'Hopital's rule. So sine would be cosine. Okay, h would go 1. H cubed over 6 would be h squared over 2 over 4h cubed for the first time. And then that's still 0 over 0 situation. So we do it again. Okay, so cosine becomes minus sine. All right, the 1 goes away. H squared over 2 becomes minus h. Yes, h. All over 12h squared. Okay, and that is still 0 over 0. Okay, getting there. Has to come to an end sometime, you hope. Okay, so then minus sine becomes cosine minus 1. Okay.
Positive.
Wait.
Positive cosine.
Well, okay. The derivative of the second derivative of cosine is minus cosine. Okay. Let's see.
Cosine should be positive.
Derivative of sines, cosine, so negative sine would be negative cosine, right?
Yeah.
Negative cosine was.
Yeah,
Yes,
because here, like to get from here to here, I differentiated twice. Second derivative of cosine has to be minus cosine.
Oh, okay,
Yeah,
yes,
because
yes,
it's two
yes.
steps.
Okay.
Because it's doing it.
And doing
Yeah.
That's fine.
So okay. So what happens in this case? But so now what happens? You know what? This is okay. I think this is where I came up with a bad example. So, okay.
So can it not be solved further, or?
Exactly.
So, okay.
It just big O 1 over H.
Yeah, which, okay, something, oh, I see the problem. I see what I did. I need to fix my example by making this a plus. Okay, so then this will become a plus, and then this will become a plus, and then this will become a plus. So now it's still a 0 over 0 situation. Okay, so now we can apply L'Hopital's rule one more time. Okay, so now we have sine by itself over 24. So it turns out the limit is 0. Yes.
So what problem was showing up because it was minus sign?
So in other words, I had given an expression here that where, and you'll see when we work it out, that the numerator would be order h cubed divided by order h to the 4th, so the whole expression is order h to the minus 1. So in other words, it would not converge at all.
Okay.
Yeah, so in order to discuss rate of convergence, we need convergence. So my sign mistake led to that. So now this goes to 0. So now what we can do is, because we need to look at this original expression minus the limit and determine the rate of convergence, but limit 0. So we can just take a look at this. So now we go back to the original fraction. Okay, so what we can do, so what should we do with this to try to find out that rate of convergence?
I mean, try 0.
So we big O of long wedge.
Well, the original one was, but now this goes to 0, so it does have a positive power of h as a rate of convergence. We just got to figure out what that power is.
Okay.
Yeah. But that's difficult to determine the way it's written. What do we do with this to extract that rate of convergence, as is done in the examples?
The expansion.
The Taylor expansion. Yeah. Okay. So the sine, the only part of this is non-polynomial. Okay. Now, to start to fill in the expansion, we want to make sure to go out just far enough. So first term of Taylor expansion of sine is h, and we see that that's going to cancel with the h here. The next term is h cubed over 6. So that would cancel there. So that would cancel everything else that's out here. We need to go one term more. So the next term can actually be a remainder term. So that would be plus. So this would be, actually I can, or what I can do is be lazy about it. The next term is h to the 5th over 5 factorial, which is 120. And then everything after that is going to be on the order of h to the 7th. Only odd powers of h have to be involved. So then this expansion goes on forever. But everything past this point is order h to the 7th. So now, any terms that cancel out, we can go ahead and do that. So there's not much left. Okay, so let's go ahead and cancel what can be canceled. Okay, and now we can divide both terms by h to the 4th. So what's the rate of convergence turn out to be? We go h, because here we have h to the 5th over h to the 4th, which gives h. Here we have this part, order h to the 7th over h to the 4th, that would be order h cubed, but it's the lowest power of h that wins, if you will, that determines the rate of convergence. That's why it's order h. So that's what I was thinking when I made up the example, my sign mistake aside, that I knew that because this part is the first two terms of the Taylor series of sine, the next term would be order h to the 5th. So I knew the numerator would be order h to the 5th. Therefore, dividing by h to the 4th would give us order h. So whenever you have functions that are not a polynomial, like a sine, cosine, exponential, Taylor series. simplify like crazy and see what's left. Lowest power of h determines it.
I might have missed it when you were talking because I was taking notes. So you write plus order h to the 7th. Is that shorthand for what the next?
Yes.
Oh, okay. I'm just making sure.
Yeah, now,
I'm not-
there's different ways you can think about it. First, I was going to put a Taylor remainder term, which would involve evaluating sine or cosine at an unknown point. But really, if you think about this expansion going on forever, like, okay, you have minus h to the 7th over 7 factorial, plus h to the 9 for 9 factorial, on and on and on. But the lowest power involved is h to the 7th.
Right. So really, what we could have done is stopped that. We didn't really need to even add in necessarily the order h to the 7th.
Well, because you could have, well, yeah, 'cause I could have done this saying, oh, this whole part is order h to the 5th. But it's a good idea to actually have this term precise.
Well, that term, sure.
Yeah.
I was remember on my homework only expanding one past what I wanted.
Well, that's all you need to do.
So okay, I'm just making sure I'm not missing something.
Yeah,
else in there.
yeah, enough to actually get the rate.
Okay, cool.
Yeah, cool.
Thanks.
Oh, something in the chat. Oh, rate of conversion anyway. Alright. Okay. Well, bring it on, I can do more.
Well, while we've got, still have time, what about the interpolation
Okay,
as well as determining the error?
okay. Now as far as like computing the interpolating polynomial, well, okay. Well, first, okay, I need to check on my examples. Okay. All right, so you need to come up with a function. Okay. So my function will be f(x) equal to square root of 1 plus x. Okay. And I need some interpolation points. X0 is equal to 0, x1 is equal to 3, x2 is equal to 8. And yes, I chose these to make a perfect square underneath. The function values will be nice. Okay. So the corresponding y values are, okay, so y0 is equal to, x is 0, so we have 1. y1, plug in x is equal to 3, we get 2. And y2 is equal to 3. Okay, so 0, 3, and 8 match with 1, 2, and 3. Okay, so what I can do with this one is work out the interpolating polynomial both ways, Lagrange form, Newton's form, and then we'll deal with the error. Okay. So we have 3 points, so that's going to give us a quadratic polynomial. So we're going to have a first y value of 1 times Lagrange polynomial 0. And then the second y value, 2 times Lagrange polynomial degree 2 index 1 plus third y value, degree 2 polynomial 2 of x. And now I can fill in Lagrange polynomials. Okay, so you know that you're going to have linear factors of the numerator and denominator. So I'll start a fraction here. Okay, so it's a quadratic, so we're going to have two linear factors up top, two linear factors down below. Now, the way this gets filled in, this first term corresponds to x naught, which is 0, and then the other, oh, the lights. It's really weird how the lights is. Okay. Whereas here, the other termination points 3 and 8. So we have linear factors for the other points. So up top, we're going to have x minus 3, and x minus 8. Because this corresponds to 0, so you leave it out. Down below, you have 0 minus 3, 0 minus 8. So the way I always remember it in my head is whatever the interpolation point this Lagrange polynomial is associated with, like where it's equal to 1, I literally say in my head, x minus the others, over, in this case, 0 minus the others. And then you have your Lagrange polynomial for this point. That's 0. So then you go to the second one. The second term corresponds to the second interpolation point, which is x equal 3. So then you're dealing with the other points, 0 and 8. So let me start the fraction. Oh, thing got messed up here. Oh, okay. All right. So, can anyone tell me what I should be subtracting here for this interpolation point?
X minus 0 and x minus 8.
Yeah, 'cause this corresponds to 3, so you leave it out and subtract the others from x. Okay? And down below, 3 minus the others. And you can see, like, okay, if I plug in x equal 3 up here, you see the numerator and denominator would totally match and cancel out and give you 1. You plug in 0 or 8, one of these linear factors becomes 0, the whole thing becomes 0 as designed. All right? We're on the third one.
X minus 0
Yeah, so x minus the others, which are
and x minus 3.
3, okay? This term corresponds to the third interpolation point, 8. Okay?
8 minus 0. 8 minus 0.
Okay. And you're done. Oh, and I'm going to put this advisory note.
We need to simplify.
No, I do not want to simplify. You know why? Because that's going to be, well, okay, I can complete the final form myself and match it. I just don't care. And I want to make sure you have the mechanics. Because also, besides, when you do do this in Newton form, it's going to produce the same polynomial. So you can say like, oh, that's the Lagrange one. So yeah, this is what I want to see, the process. Is this a Math 101? Not interested in your distributive property skills. Okay. All right, questions about Lagrange form? Okay. This is nice. I wasn't expecting that I would come in here, ask you all questions, someone had a few questions, and then we stand here awkwardly for 10 minutes, and then we all quit. You guys are making me work tonight. Okay. Things I didn't expect, but that's good, you know. Asking the right questions. So Newton form. So for this we need a divided difference table. Okay, so need to set that up here in LaTeX. Let's see, we need the x's, the y's, and then that's 3 rows, 2, 1. So I need 4 columns altogether. Okay. So the first column will consist of the x values, so 0, 3, and 8. Okay, and then the second column will consist of the corresponding y values. Okay, actually I'll put in some column headings too. I, then the 0 order divided differences. Okay. All right. So then for the third column, which would be the first order divided differences, then these points are all distinct. So okay, I'll just write out what the fraction will be so you can see where it comes from. All right, so I have 2 minus 1 divided by 3 minus 0. Okay, so we get 1/3. Okay. Then I have down below, okay, so 3 minus 2 divided by 8 minus 3, so that's going to be 1/5. Okay. And then we have just one divided difference left, so it's going to be this minus this divided by these two extreme x values. Okay, so all right, so I have 1/5 minus 1/3 over 8 minus 0. And see why it is, like, if you go through your divided difference table, like, backtrack along the diagonal, like, go up to here, and see, oh, what's the x value? Go along here to get 0. Here you backtrack this way through the divided differences, and you wind up at 8. So that's how you know it's 8 minus 0 that goes in the denominator. Okay, so now what we have here is going to be, okay, so 8 denominator, so it's going to be minus 2/15. That's annoying. Okay, so it's going to be whoops, where'd it go? Okay. And then the divide difference table is complete. What I'm going to do here is, why I have asked, I look at Matlab. Zero. Oh, okay, so I can prove my Matlab that this is correct. Okay, so now you need to write the polynomial in Newton form. So for instance, if you go along the top row of coefficients, we have 1, 1/3, and minus 1/60. So P2 of x will be equal to this divide difference, so 1 just by itself, plus the second divided difference, which is 1/3, times x minus the first point, that'd be 0. And then I have minus 1/60 times x minus 0 again, and then times x minus the second point, x minus 3. All right. And again, no need to simplify, I'm just doing it because. It's going to be x squared minus 3x. Okay. Okay. So, and you go either way, either top row or bottom row, as long as you use the correct points. So I'm using the top row, you start from the top, work your way down. The last point would not be used. Just these two. Every time you tack on a new term to Newton form, like whatever divided difference you're adding on, that brings in the next point in your linear factors that you put in here. One thing you can do, and you certainly have time to do it, is once you have a polynomial, go ahead and plug in the x values. Do they produce the y values? If they do, well, that's correct, because the interpolating polynomial in whatever form is unique. And argue with that. Okay. Now here I'm doing both forms for the same example, but in the test, you'll have like one function you do a Lagrange form, and a different function you do a Newton form. Any questions about Newton form? And lastly, the error. I think we'll cover the entire test at that point. All 5 tasks. Okay. Okay. So I'll just well, down here I have the general formula, so I'll just bring that up here. So now I will fill in this case, n is 2. And then we can deal with getting an upper bound. Okay, so now I have f triple prime at an unknown point over 3 factorial. Then I have my linear factors for my interpolation points. So x minus 3, x minus 8. Okay. And so it's f minus p2. Okay. So, to find an upper bound on the error absolute value, and let's just say on the interval 0 to 8. Because that's the interval that contains all of the interpolation points. So there's two parts to this. Okay. So the first part is an upper bound for third derivative. We need the derivatives of your function. So we start out with 1 plus x raised to the 1/2 is the original function. Now it's going to keep taking derivatives. So I have 1/2, 1 plus x raised to the minus 1/2. Okay, that's the first derivative. And then I keep going, unfortunately. 1/4, 1 plus x to the minus 3/2. This is going to be tossing. Okay. So first derivative, second derivative. Okay, then the third derivative. Okay, so now I have 3/8. 1 plus x raised to the minus 5/2. Okay. Now, I will give you guys a little flexibility here. I'm not going to require the absolute sharpest upper bound you can get. So here's one thing you could do is, since this is the third derivative, so this is what I want an actual bound on. So this is f triple prime of x. So what I could do is take the derivative of this and find critical points and all that. Well, actually, there won't be any. Because x is between 0 and 8. Because your next derivative is going to be another constant times 1 plus x to the minus 7/2. It'll never be 0. So that helps. Because if you determine that the function is like always increasing or always decreasing on the interval, you can just plug in extremal x values, like plug in your endpoints. So if you know that about your function, that helps. Or like, for instance, suppose you did it with sine or cosine. You can just say, okay, well, sine or cosine is less or equal to 1 in absolute value, so you can take that into account. So I will accept any reasonable upper bound. Yeah, so I mean, you can always do the whole thing, take a derivative, set it equals 0, find the critical points, test the endpoints. But I'm not requiring you to go that far. But if you do something like I give you a function that's fairly small, like say x squared from 0 to 2, and you give an upper bound of 10,000. That is an upper bound. Yeah. But you consider like, okay, x squared of 0 to 2 is increasing, so you just plug in x equals 0, plug in x equals 2, and you get an upper bound of 4. Okay. Now, so this is 1 plus x to a negative power. So what we can conclude here is that on the interval 0 to 8, f triple prime is decreasing because we have a negative power of 1 plus x. So the maximum, and it's always positive too, so maximum is 3/8. So that is the upper bound for this part. Now, C is an unknown point between 0 and 8, because it contains the interpolation points. But we know that 3/8 is a valid upper bound for this part. And really, we can't, based on the information we have, we can't do any better than that. That's the sharpest bound we can realize. So questions about that part? Okay. All right. The upper part is finding upper bound on, I should say for the previous part, that's the upper bound on the absolute value. Let's put that in there. All right, so now we want the upper bound on the absolute value of the upper part, x minus 3, x minus 8. Okay, so here too we can look at critical points. There's no need to look at endpoints in this case, because we know that the value will be 0 there. Okay, so we'll look for critical points. Okay, so we have, what I'll do is, I'm going to cheat. This polynomial has roots 0, 3, and 8. So, if I multiply that out, that's x cubed minus 11x squared. Yes, I have Matlab do this for me. X, okay. So now I take the derivative of that, and I get 3x squared minus 22x plus 24. And I'm using Matlab to compute the roots for me. Believe it or not, they work out fairly nicely.
Yes, 1 is 6.
Roots 4/3
3 whole.
and 6. And both of those, both of these fall within the interval 0 to 8, so we can consider them both. Okay, so now if I plug those back into the original, okay. And yes, I'm using Matlab right again. So there may not be Matlab on the test, but you can use Matlab to help you with the computation part or calculator, whatever you want to do. I don't think I need an auto calculator. I just use Matlab for everything. Okay. So if I substitute the roots in there, x minus 3. And what you get is, okay. Has a maximum absolute value of 36, because one of the roots gives you minus 36, the other root gives you like 14.8 something. So 36 is the largest that this expression can get. So like it actually, you can see that if you plug in x equal 6, you get 6 times 3 times minus 2. So you get minus 36. Okay, so now we can wrap up. Okay. Whoops. Stop it. Is okay, so from the first part we had 3/8 divided by 6 times 36. So that's 6 times 3 over 8. So that's 9 fourths. All right, so that is how large the error can possibly get on the interval from 0 to 8, which is not that great. Although the true error probably is smaller, like but it's because we're taking upper bounds of this part and this part separately, and then multiplying them. But because this point is unknown, so we can't do anything more than that. Okay, so questions on the error bounding process? I should make clear that what I was doing here was expanding this out. Or other questions?
Is the plan for us to still get the test like Wednesday evening, or is it Thursday?
Okay, the test is nearly ready. I do want to make sure to check it, because the last thing I want is to have a mistake on a problem. But yeah, I previously said that the test would be posted by class time on Thursday. I am open to posting it sooner, as long as I make sure the content is solid. When I do post it, I will send a Canvas message, so you'll know. And I'm not gonna like quietly put it out there.
Does it include the tag files?
I will include the text file, sanitized text file with a PDF.
And then about approximately how long will we have to do it?
I'm sorry, what?
Sorry, mute cut out there. Approximately how long will we have to do the test after you post it?
Oh yeah, that's something I've already stated, that the test will be due Friday, October 15th at 11:59 p.m. So you have a minimum of 30 hours and 30 minutes to do it. And I do need to be firm about the due time though. And the reason is that I want to grade it over the weekend. And then and have it back to you all by class time on Tuesday. Other questions? So you're welcome to use whatever resources, but those resources do not include other people. And that'll be stated on the test. I don't like to talk about these things, but I have to. Like for instance, if I see certain similarities, some similarities are to be expected. Some are not, and I best not elaborate. But sometimes I have detected a clear pattern of collaboration. And if I see that, then I reserve the right to look into it, and it's something that I will act upon. So just don't do it. It's not worth it. Because we have a thing here. grade called XF. It cannot be removed from your transcript by retaking the class. So on that somber note. Alright, well, I'll stick around in case anyone has questions, but we can stop here.